Okay, crowd. So these are Antonio, Jacopo, and Andrew from the Shellphish team, which is from the UC Santa Barbara. And they will talk to you today about a dozen of years of Shellphish. And I have to read the subtitle, from DEFCON to DARPA Cyber Grand Challenge. And yeah, how they automatically exploit stuff. So thank you. Give a warm applause.
All right. Thanks a lot for the intro. So I'd like to continue with saying, who the hell is Shellphish? So Shellphish is a team of security enthusiasts that has started in UC Santa Barbara some time ago. Now, the original version of this slide actually said that Shellphish is a hacking team and there are lots of Italian in that, but then my colleague Antonio pointed out that putting hacking team and Italian could have, maybe they shoot us or do something bad. So we are not related to that hacking team. We actually, most of us do research in system security. What it means is that we are based, many of our team members are based in research labs, and they publish papers that try to improve the state of the art of what is known in computer security. But we also play, as Team Shellphish, many capture the flag competitions. As a matter of fact, we have even released a couple of the tools that we use both in system security and in capture the flag competitions. Some of you may have used in the past the publicly available Anubis and Wepawet, so you could submit a binary or a website and see how they worked. And today we're also going to speak in a little bit more detail of Anger, a tool that we have released, that team members in the lab that have worked on it have released recently. So just to brag a little more, who is Shellphish? Shellphish was born in that little building in the UC Santa Barbara, well known as the only university that owns a private beach, and that has a reputation as a party school. I actually got this comment from a flight attendant on a flight, so it definitely has some bad reputation, but believe it or not, it's actually a very good research university that has employed several Nobel Prizes, none of which are in this room. And the Shellphish team has also expanded through its alumni to other research labs, such as people in Boston who never see the sun, and Eurecom in France, in Europe. And as you can see, we are a relatively international team. We have the majority of players are originally from Europe. Of course, we have a good representative of people from the US, some very great hackers from China and Asia, Brazil, Senegal, and unfortunately, we have no one from Oceania. If you want to, we are very open to recruit people, join one of our research labs. As a team, as I was saying, we play CTF. So I'm sure many of you have already played Capture the Flag competition, so I'm just going to give a very minimal primer that is going to be useful for us later. CTF is a security competition in which you are presented with a challenge. It can be a binary program, a service, a website, sometimes even a hardware device. And there are many variations, but the basic idea is that you understand how that works, you find where the secret is, you steal it from the other guys or from the challenge, you submit it to the organizers, and you get points. And Shellphish has participated in many CTFs, including the DEFCON CTF. It has even won the DEFCON finals in 2006. None of us were actually on the team at the time, but it's in a sense, good memory. But we do not only play CTFs. If you may be familiar with the UCSB ICTF. ICTF is an attack defense CTF in which you not only crack programs to steal the secrets from others, you also have to defend yourself and patch the binary so that other teams cannot steal secrets from you, but the service is still functional. And Giovanni Vigna was the originator of the ICTF. It used to be, as a matter of fact, the final of the security class of Giovanni, and it has evolved many, many times over the years. The ICTF has, in many ways, tried to innovate with a different style every year. Some years have worked very well. Some other years have not worked that well. we have, in a sense, we have had many, many discussions even internally, I can assure you of that, but we have, in a sense, embraced the nickname of chaotic shitstorm. And we have gone with the very, in my opinion, very brave and very good attempts to innovate. If you have played in the last years, for instance, you know that we have tried to give higher importance, emphasize the importance of network defense, for instance, or try to see what teams would do if presented with a huge number of 42 services, and to see would they try to sort of defend all of them with the same approach, attack all of them with the same approach. And in the latest year, we've even gone with the full player versus players, player versus player. Even the programs themselves were written by the players of the competition itself. So if you want to hear more about the ICTF, our base framework is the base framework that we use for the competition has been released in open source. We're in the process of preparing the new version. And you can also read our paper of 10 years of ICTF to get a little glimpse of what has been done over the years. But now let's get back to the juicy stuff. So why the hell are we here? Why should you be listening to us? Basically, we want to show essentially how you can go from this to this. And we've been told this is a very American style slide, and I say, Jacopo, Antonio, you guys have really gone American if you're showing this, but I'd like to have you know that most of these notes are actually $1 and $5. I think there's a $5, yeah, that's down there, so it's not actually that much money, but Shellphish actually, no, on a more serious note, Shellphish actually has won some money by participating to the DARPA Cyber Grand Challenge, and we're gonna explain a little bit to you what that is, what it involves, and then we're gonna go a little bit more in detail and give you an idea of how we decided to play the competition. And we're gonna give, not all the components obviously are public for obvious reasons. We don't want to make the life too easy for our competitors, but we're gonna give you an idea of some ways that you can use to automatically discover vulnerabilities. And in particular, we're gonna give you a live example using Anger. Anger is an open source binary analysis framework that can do many things, even more than we have used for the CGC, and obviously many more than we're gonna show you in the live demo. And it's an open source framework that you can use yourself. As a matter of fact, if you're interested in Anger, and so also becoming very rich, you can join us later after this talk. We're gonna organize a workshop. Andrew is gonna be in charge in hall 13, 1-3, it's on the first floor. So if you want, you can join us later. We'll give you more details about that later. And finally, we're gonna give you a hint of what are the next steps that we're gonna take, that teams are gonna take to participate to the finals of the Cyber Grand Challenge. As you can see, we're also very fond of acronyms like DARPA. So let's start with a basic idea. So I think most of you guys have heard of DARPA. DARPA is a research agency by the part of the Department of Defense of the United States of America. Many of you may be familiar with the role that it has played in the creation and evolution of the internet. And DARPA's mission is, in a sense, to, among other things, push forward research in approaching interesting problems. And occasionally, probably the most famous one that you may have even heard in the press is that in 2004, they started a grand challenge. No one was able to do it before. Make a car that can start at a certain point and alone, completely alone, autonomously drive from point A to point B. And you know, nowadays we hear there are many very good projects on making self-driving vehicles, many of which are actually realized. In 2004, believe me, it was not easy at all. As a matter of fact, in this 2004 Grand Challenge, none of the vehicles actually reached the finish line. So in a sense, DARPA has, in a way, found a problem that no one was solved and tried to push forward to see, I challenge you, can you show me what you can do to face this challenge? But now, as I was saying, there are cars that do that. So now in 2014, DARPA has decided to start the Cyber Grand Challenge. And once again, it means completely autonomous thing, completely autonomous exploitation and patching other programs. And yes, what you see right there is a competitor. So as a team, you'll have this array of servers, free to do whatever you want with them, but you have to play a game. And the game is what we're going to talk in these little next slides. But first, let's just give you an idea of the current progress of the competition. The qualification has already taken place. It was in June this year. 7 teams originally joined the challenge, and 7 teams have been selected as qualifiers after the qualification event. The finals will be August next year and will take place at DEF CON in Vegas the day before the DEF CON CTF finals. And as a matter of fact, the winning system will play against the humans. And let's hope for the best that the humans still win, because otherwise we're going to have quite a bit of problem. And we're going to go a little more into details, but if you want an intro, in a sense, a more usable intro, DARPA has a very nice website, very flashy in a sense, at cybergrandchallenge.com. So let's talk about a moment more about what is the CGC. So no surprise, it's an attack defense CTF, exploit, patch. And again, as you can probably imagine, the way you participate as a team is not that you're given a program, you look at the program and you exploit it. And it's not even that you look at that program and you write the program that exploits that guy. It's not that you write the Python script that exploits this specific program. What you need to do is you need to develop a system that is going to be fed some programs and automatically, without human intervention, will find vulnerabilities, exploit, and patch them. Okay? Sounds simple, sounds easy. It's not that much. It's actually interesting. I like you to take a moment and how would you play? What would you do? It's an interesting question, and it's what in part led us to work on this. But I would like also you to reflect for a moment that this is also not that trivial to organize. And I think DARPA, in a sense, merits some praise in the sense that they have had to take some interesting choices. For instance, how will you prove that a binary was exploited? Now, as you were saying before, in classic CTF, you're given a binary, and maybe the binary, there's a file called flag, you need to read the flag, or you examine the thing, you see, oh, there's a winning message and there's a losing message, I need to make the program print the winning message. Or maybe it's a storage server and the secrets are the secrets that are stored in these files that have certain names and so on and so on and so forth. As you can imagine, this is a lot more complication for a program to analyze. This is useless complication in a sense. So DARPA introduced for the quals, for the qualification round, a very simple way to define what is an exploit. You have exploited a program and you demonstrate that you have exploited it by giving an input that will crash the program. Segmentation fault, whatever. If you the benign program will not crash. If you make the program crash, good. You found an exploit and you're going to get the points for the exploit. Easy? Is it easy? Well, don't forget that the competition also includes a defense component. So what do you think is going to be the defense? Is it just going to be that the program just needs to run until the end? I mean, if it doesn't crash and it doesn't time out, it's good? I mean, obviously you could say, well, yeah, that would work, but then I can just submit this as a patch program and believe, this is what is usually, if you have played some CTFs, you may have heard the term the Superman defense. Usually in this competition, you want to avoid, organizers and even players, of course, want to avoid defense systems that work every time, in a sense, no skill required, or very little skill required, or in a sense that work in every binary. So how do you prevent this from happening? Well, this one is relatively easy. Basically, you need to put in some functionality checks. So that means that whoever writes the program, not only you write the code of the program, not only you put in a vulnerability in the program, you also need to put in some scripts that will check the functionality of the service. For instance, if the service is a palindrome finder, you need to write some script that send words and see if the program correctly says palindrome, not a palindrome, and goes on. And of course, you also want to make sure that these checks are in a way meaningful and not easily patched. For instance, if the program just admits 2 good value of inputs and 2 easy answers to those 2, or even complicated answer, then you want to avoid that. The team can patch just by making an if this input, then this output. If this other input, then this output. Otherwise, exit 0. So again, this takes a little bit more skill than it sounds. Ooh, this was a secret. No. What is another way that you can build a Superman defense? Another way is that you could have what is called a out-of-band error handling. So you're running the service, you're running the program. The program, for instance, tries to use a unmapped address, and the program is going to get a segmentation fault, and ordinarily this would be considered a crash. But if I can install a signal handler, then I can turn all these crashes into benign exits. And since I know that for benign inputs, the program will never do a zigzag, I'm sure that I can do exit 0 without compromising the functionality check. So once again, Superman defense. My program cannot be exploited. And the solution for this is that, in a sense, or at least the solution that DARPA took for this, is that there is no out-of-band error handling. There's at least no easy way to do out-of-band exception handling, error handling. But as many of you may be familiar with terms such as DBT or an emulator like the MAME, for instance, the emulator for consoles, what would prevent me from writing an interpreter? Okay, so I don't actually run the x86 instructions, you understand? Like, I can run these instructions in my little VM, my little VMware or VirtualBox or MAME, and whenever I detect that the CPU would raise an exception, for instance, because it's, again, segmentation fault, out of band, accessing unmapped memory, division by 0, whatever, again, I'm going to exit 0. Now, please take a moment. How would you prevent me from doing this? It's not as easy as it sounds. And DARPA, in my opinion, took the elegant and also very correct solution. You don't. This is perfectly allowed in DARPA CGC. The point is that you pay for that. So sure, you can do whatever you want. You can even write an entire binary translation platform. In fact, one of the qualifying teams, non-qualifying bits, sorry, trail of bits, actually did something close to this. We obviously don't know the full details, but they did a translation to an LLVM intermediate, and they went back, and I encourage you to read the blog post from them, because they, but not because it's a stupid way, it's actually a very good way, and you will see that, in a sense, you run into a risk that you need to make a very good estimate of what's the cost of the defense that you're putting in. If the defense that you're putting in ends up consuming too much CPU or maybe too much memory, then you may lose points in your, even if your defense is perfect in itself, you may have lost points in this. And I'm just going to give you a couple of extra ideas of the competition. Obviously, you want the competition to work on realistic programs. You want programs that can do more or less what the programs that we run on our laptops can do, so no hello world only. But you also don't want extra complication. And what do I mean by this? It's a little fuzzy as a term, but basically you need to think of this, that the advantage, the work that the teams are going to put, and the advantage that you're going to take by looking at how they do things, teams have a limited amount of time. So do you really want the modeling, the team to spend a ton of time modeling the entire, horrible things like interruptible syscalls, or an entire model of file system, and so on and so forth? So usually not. You need to find some sort of compromise. And again, I think DARPA found a good compromise here. The architecture that is being used is regular, Intel x86. all opcodes, all userland opcodes at the very least, are fair game. So all the problems that I'm sure you're familiar with, such as problems in disassembly and so on and so forth, are all there. So it's very realistic. But the OS is a somewhat limited form of a Linux-like, Unix-like operating system. As you can see, you have some basic syscall, transmit and receive. They're basically read and write from the standard in, standard out, and sockets that connect programs together. You also have a form of select that also allows you to sleep, wait. You have some form of malloc and unmap, so to speak, but these can even allow you to map executable code pages. So if you want, you can even write a just-in-time compiler in this architecture. You have randomness. You have the way, obviously, to exit the program. Probably the biggest simplification with respect to the capabilities of a full real-world Linux program is that there's no shared memory, no threads with shared memory. Particularly interesting, at least to me, is that DARPA took the bring your own defense approach really to the maximum extent. So you do not even have, by default, the usual, so to speak, the defenses that are common nowadays. So the stack is executable like it was ages ago. There's no ASLR, there's no nothing. You want this stuff, you have to bring it. You have to patch your program, modify your program so that it has them. I think it was an interesting idea from DARPA, and as we have seen in the Trail of Bits case, this brings with itself some non-trivial choices on the team side. So now I'm gonna pass the torch to my colleague Antonio, who's gonna introduce a little bit our cyber reasoning system, so the way we play the game.
So that's good. Okay. So I'm going to introduce the cyber reasoning system we developed. What is a cyber reasoning system? Is just the way DARPA defined the system we had to develop to participate to CGC. And so, as Jacopo introduced, as an input we have a list of binaries. And for each one of these binary, we need to produce an exploit that is an input that is going to make this binary crash, and a patch version of this binary that is immune to these exploits, but still preserve at least some functionality. And so let's see our system a little bit more in details. So we have basically the vulnerable binaries are passed to an automatic vulnerability finding component that is, as the name says, trying to automatically find vulnerabilities into these binaries. And then both the exploits generated by this system and the vulnerable binaries are passed to an automatic patching component that is trying to generate the patched version of these binaries. And of course, and some of the patching strategies actually require exploits to generate patched version of a binary that are immune against a specific exploit. So that's the reason of that arrow. And both proposed exploits and proposed patches are evaluated by another component that is evaluating them in terms of how good a patch version is. Is it preserving functionalities? Is it crashing because there was some bug in our system? So we are evaluating this. And of course, the best exploit and the best patches, the best patch we have for a specific binary is finally submitted to DARPA for their evaluation. So that's the general idea of our system. And for the next of the presentation, we are going to focus on the automated vulnerability component. And so let's see what we did. So here, for the qualification, remember that an exploit is just a program that is making, it is just an input that is making your binary crash. So that's the question we want to answer. How do I crash a binary? But this question is somehow a subset of a bigger question, of a much more difficult question. It is, how do I reach a specific state within the execution of a binary? So this is an undesirable problem in the general sense, but there are some approaches that can solve this problem in a good amount of cases. And so these are the two approaches we used. So one is fuzzing, and the other one is symbolic execution. So let's see first how these two approaches work in general, and then how we use them. So about fuzzing, so as I say, the question we want to answer in general is how do I reach a state within a program? And if you see at this code that I put in the slide, we have a very simple program that is getting an input from the user, putting in a variable hex, then it does two different checks, and then it can either print you win or you lose. So suppose that we want to understand how the text you win is printed, which is the input we need to provide to reach that state. So of course, the easiest thing we can do is just to test a lot of inputs. So we can try with 1, and you lose is printed. We can try with 2, still you lose. But when we try with 10, we will reach that instruction. So we will reach the state we were looking for. So fuzzing is in the simple way is just trying a lot of different inputs. But specifically for CGC, we use fuzzing, and we use a way of a method called coverage-guided fuzzing. That means that the execution of the program was executed in an instrumental environment that was taking track of how much a given input was covering of the entire code base of the binary. And this system was focusing on basically on those inputs that were more promising. So those inputs that were increasing the most the general coverage of the program. So our system was based on an already existing system called AFL. That's the link to the original version of AFL. And this system was really was effective. But there are specific cases in which this system cannot work, or at least cannot work efficiently. So let's see an example. So here we have the same code as before, but there is one difference in the second conditional instruction. So here x needs the square of x needs to be equal to that big constant value. So of course it's really unlikely that just by trying a lot of different inputs we will actually find by luck or by any method the specific solution of that equation. So as a possible solution, we can use symbolic execution. So let's go back for a second to the original example. So the general idea of symbolic execution is to interpret the binary code and replace user input with symbolic variables. So the first instruction is getting some input from the user. We don't know what the user is putting here in the general case. And so our symbolic execution engine will just keep track of this by putting a variable x within the current state of the execution. So then we go on executing the program normally. And but of course, if we reach a conditional instruction like this, we don't know which of the two branches we need to take because we don't know the value of x. So what we do here is that we take both branches. We take both branches, but we keep track of the constraint that a branch is putting on a specific path. So in the path in which in the first branch of this conditional instruction, of course, if we take it, x needs to be bigger or equal than 10. And in the other, x needs to be less than 10. So the execution goes on, keeping track of these constraints. So suppose that now we symbolically execute starting from the state on the left. So now we encounter a second conditional instruction. And as before, we generate two different states. In one, x, we have an additional constraint. We have an additional constraint that says x needs to be less than 100. And in the other state, we have a constraint that says x needs to be bigger or equal than 100. So, but now we reach actually the condition we were looking for. That is, in this case, the text you win is printed. So when we reach a condition that we were looking for, we can ask to the symbolic execution engine to actually to concretize this input. That is, to give us a to give us a concrete value that satisfies both constraints, in this case 99, and if you in fact put 99 as an input, you will reach that condition. And of course, if we go to the more complicated example, for the symbolic execution engine is not that complicated to deal with this. We just have a different constraint, but still any symbolic solver can still solve these equations and give the correct answer that is 1, 2, 3, 4, 5. So we use symbolic execution for CGC. In particular, we use the symbolic execution engine of Hanger, that is the binary platform developed, the binary analysis platform developed at UCSB. And in particular, we were looking for two different conditions. So one is memory accesses outside allocated regions, and the other was unconstrained instruction pointer. So unconstrained instruction pointer means you have, for instance, a jump instruction that is jumping to the value of a register, but the value of that register is coming from the user input, so the symbolic execution engine doesn't know where to jump. So why we were looking for these two conditions? Well, because if you reach one of these two conditions, it means that you also found a crash, an input that will make the program crash, either because the program, given that input, will access not allocated memory, or will just jump to non-existing code. And so as a general idea, so for the final, we are exploring the idea of combining the two approaches. And in particular, a paper has been accepted at the NDSS conference, and it will be published in February, and it will be presented in February at the NDSS. Just to give you a preview of the results of that paper. So if these are the entire binaries we had to solve for CGC, for the qualification, these are in scale, more or less. So these are the amount of binaries we found. We can find an exploit using fuzzing. This is the amount of binary we can find an exploit using symbolic execution. But combining the two, we can find even more binaries, even more exploits. And so the bigger circle is the amount of binaries we were able to exploit using this new approach. So I suggest you to read the paper as soon as it will be public. So, OK, now Andrew will introduce Hanger, and he will give us a live demo. Good.
Hello, I'm audible, good. I'm going to talk about anger. I'm the angry one. Anger is the Python library. You use it. It has code. You can run the code. And it does binary analysis. It does all the things that Antonio just finished talking about and more. It's open source because we believe in that sort of thing. And it's interesting to note that Anger started because of one of the other graduate students in our lab wanted to do a project on firmware analysis and got carried away. And since then, that project has grown and become adapted to CGC and Linux binaries and all those different architectures. So it's had the multi-platformness baked in from the beginning. And I said it is written in Python. This is just because we're a research lab. We need to move fast and break things. We don't really have the luxury to program in something like C++ or OCaml, not that we'd ever want to. And because of the magic of Linux and the Python package index, you too can have it with those one or maybe two commands. One is if you're willing to forego the support we are providing you. So what I'm going to do here is I'm going to demonstrate using Anger to automatically find vulnerabilities. The automatic part is, we'll see. So we're going to show off finding the grub back to 28 vulnerability, which you may have seen recently. There's been a lot of news coverage about a vulnerability in the Grand Unified Bootloader versions 1.98 through 2.02, that if you press backspace 28 times and then return on the grub password username prompt, you will get a rescue shell, which is an interesting vulnerability, and it is due to an unchecked integer underflow in the username and password input function. So as you can see on the screen, there's a link to the actual write-up of this vulnerability, which we copied a lot of stuff from for the explanation. And the specific vulnerable part of the code doesn't check underflows. It just simply decrements the index into the current input buffer. So then later in the function, what it does is it clears the unused parts of the buffer with this memset command. And the problem is that you can make the current length negative. So if you make the length negative, all of a sudden it's memsetting other parts of the stack, like the return address. So once it sets it all to 0, then the program is going to jump to 0 and crash, except that this is in x86 very low-level stuff, and somehow this is possible. The explanation of why this can be exploited successfully is well outside the scope of this talk, but please read that write-up, it's very nice. So finding this automatically is going to be very difficult because, as you see there on the screen, is a control flow graph of the vulnerable function in the grub binaries. And as you can see, it's got a big loop with a whole bunch of paths. And if you take a symbolic executor and throw it at this problem and say, find me a crashing input, the universe is going to grow old and die before anything interesting happens. It's too much state. You're going to go through the loop once, you're going to produce 10 successor states, each one of which has gone through the loop. Then each of those 10 needs to be put through the loop again, and they will all each generate 10 children, and you're going to have an exponential state explosion, and your computer is going to run out of RAM realistically. So I have a demonstration here of the naive approach of symbolic execution, the grub naive script, which is just using anger as a naive symbolic executor. So most of this is simply setting up the grub state, because we realistically cannot execute symbolically grub from the very beginning of program boot. So we choose to start our execution in the program. This is something that anger can do. You can construct your own state, which is the line that does the state construction. It's down here. It just constructs a blank slate blank state that you can use to symbolically execute as symbolically as you like. And then it simply steps the path group until it finds something that has jumped to 0. And as we see here, I've also set it to print out its current internal anger state at every step. We can see that very quickly it's starting up, it's executing lots and lots of symbolic states. You can see the active number is becoming larger and larger as the program slows down more and more. And if we look at my memory consumption, we can see that it's slowly going up and it's going to run out eventually. We're not going to let it get there because I like this computer. So in general, the security community has attempted to solve this kind of state explosion problem in loops with a technique called veritesting. That's from a Carnegie Mellon University paper. Anger implements this. I tried it. It doesn't work because it simply generates too much complexity for the constraint solver to handle. It's a bit more of a technical discussion that we can have later in the workshop. However, anger does let you solve this problem because symbolic execution is powerful, but it's really dumb. It's going to spend all this time computing things that don't need to be computed. So you, on the other hand, you are very clever and you know how to smartly navigate the state space of this program in order to not waste your effort, but there's no way that you could realistically do that with the precision and care of a symbolic executor. So the solution is anger. Anger provides an interface for you to channel your anger effectively. Search your feelings, you know it to be true. So what you can do in order to solve this vulnerability, this is what I did last night to prepare for this demo, is to manually examine all of the surplus of symbolic states that anger produces and figure out what's going wrong. And you can see that it's doing all sorts of things that you would never do if you were personally exploring the state space of this program, like entering several letters in a row and then deleting them or pressing the home button multiple times in a row. You don't need to do that. Yes. So what you can do is you can just tell anger to not do these things, and anger provides the power of anger is it provides reasonable interfaces for you to do this more easily. I took my previous example, the naive approach, added 10 lines of code, and it finds the bug, as we're going to demonstrate. So we say grub bug, and it still prints out, but now we can see that it's finding a whole bunch of not unique paths that it's discarding. And now the computation load is very easy for the symbolic executor process, and it finds the crashing input, which is 28 backspaces in a return. So that's all I have for the demo. Just a couple of side notes that this is, if you look at the script itself, you can see at the top it's straight up loading the grub executable out of my operating system. I haven't done a system upgrade in several months, so I'm still vulnerable. Please don't hack me. But what I was previously doing is I was previously trying to exploit the 64-bit version, and it didn't work because this exploit doesn't work on 64-bit systems because of the way the compiler uses RAX versus EAX, and it's a mess. But I didn't know this until I had written the entire exploit and found that it didn't work. So after a little bit of manual analysis, I realized this was the reason, so I just switched over to the 32-bit version, and all I had to do in the Anger script was change the word sizes and the program address. Anger is incredibly versatile, and it can handle all different kinds of programs. It can handle binary blobs, it can handle firmware images, it can handle PE and ELF and maybe Mako files. And I don't know, my opinion is the power of anger in the interface, and I recognize that this is a very dissonant message from what we were talking about earlier with the automated hacking stuff, but the point is that this is why the Cyber Grand Challenge is hard. The secret sauce in our CRS is not something that we can talk about under penalty from my professor, can't do it, and that's so I'm emphasizing how user-friendly anger is because that's the way that you're going to be using it. We're going to be using it as an automated system, which is a lot of really complicated algorithms. That's all I have to say. Back to one of the two, I forget which, to talk about the finals of the Cyber Grand Challenge.
So let's go back to something a little bit less technical. So we played the qualification, 7 teams best, as Jacopo said. Shellphish was one of them. In particular, we exploited 44 binaries out of the 131 provided by DARPA. And every qualified team received $750,000 as a prize, so that is a good thing to have. And okay. So for the finals, the setup of the competition will be different. In particular, many things will be different. So the finals will be a round-based attack defense CTF. So for the qualification, we just receive all the binaries, and then we had 24 hours to automatically find exploits, patch them, and submit these patches and these exploits to DARPA. Instead, here it's a round-based attack defense in which at every round we receive new attacks from other teams, and we can submit new patches. So this is not 100% finalized right now, but there will probably be no possibility of human intervention or very limited possibility of human intervention, whereas during the qualification phase, it was at least possible to fix bugs. For instance, if you forget to put a file as executable because you didn't sleep for the previous week. So something like that. And maybe there may be some possibility of bug fixing even during the finals, because of course everyone wants to avoid that you work for 2 years on something, then you forget a semicolon, and all your work is pointless. Since something like this happened for the Grand Challenge with cars, so they may want to avoid this somehow. But they don't want you to adapt to exploits sent by the other teams, so you need to balance these two things. So another interesting point is that data about previous rounds is available. So first of all, you submit exploits and patch version of binaries, and you can get from the system the performance they have. So you can adapt based on that. But also anonymized traffic sent by other teams against you, you can receive it and you can analyze it. And you can even receive at every team patches that other teams, patched version of binaries that other teams submitted. So this brings to a lot of interesting scenarios in which you may be able to steal patch binaries from other teams. You may be even able to steal exploits. So there is some, probably some metagaming you may want to do about deciding how to patch, what to patch. Maybe you can just steal a patch and wait before deploying your patch. We don't know yet, but there may be some metagaming. We need to reason about it. And yes, also this is important. So exploits are going to be different. So for the qualification, an exploit was just an input that was making your program crash. For the finance, there will be two different types of exploits. So the type 1 is basically an exploit is some code that receives a specific location and specific register and a specific value from the organizer. And then this code generates an input for a binary that is making the binary crash at that specific location and also setting a register to a specific value. So this is somehow a way to, the DARPA has to check that you kind of reach a state in which you actually exploited the binary. So the binary is under your almost full control. Also, another kind of exploit is a type 2 exploit in which you have to leak data from a specific memory page provided by the organizer. And so for this, we will need some more realistic exploit generation. And we are working on using Hanger to do something different, that is to automatically generate a ROP chain as a part of the exploits. Also, as an addition to all of this, there will be the possibility to deploy network-level filtering rules. So during the competition, there will be an intrusion detection system for which you can provide rules that prevent traffic to reach your services. And for instance, a rule can be if a packet has this string, just block it. But of course, you want to deploy these rules, but in a way that you are not impacting the functionality of your services. So this is a completely new area we have to explore. So every team has access to a cluster of 1,280 cores, 16 terabytes of RAM, and 128 terabytes of storage. This is a picture of one of it. And so right now we can access to this through SSH, but for the final, they will bring 7 of these, to one for each team to the hotel where DEF CON is. And so it seems that they will also bring a 0.5 megawatt generator to power all these things and cool them. And so, of course, the first thing we did when we got access was to run htop. And then we spent other 2 hours trying to run htop on all of them at the same time, so using Terminator. And yes, that's a huge screenshot of like 5,000 pixels, something like that. So, okay, so finals will take place in August 2016 at DEF CON Las Vegas. There will be money prizes. So the first place is $2 million, second place $1 million, third place is $750,000. And as Jacopo said, the winning team will compete against human teams at DEF CON CTF finals. And it seems that the winning team will have access to the entire 7 clusters. So the winning team will have access to something around 100 terabytes of RAM, something like that. So, and we'll try to compete against humans. So we don't know. So because of this, it seems that next year, DEF CON CTF finals, all the binaries for the finals will follow the CGC format, so that humans and these automatic systems can play against each other. And so I just want to conclude with a picture with all of Shellphish persons that contributed for the qualification. You can also see my Photoshop skills. And so then, since the qualification, other 2 members started working on this. And as you can see, we are from all over the world, and Italians, the number of Italians surpassed the number of Americans. And okay, and so we will have a workshop after this talk in all 13. And so let's bring your laptop, and we will show you a lot of things. So all 13, I have a map, but it's really hard to find rooms here. So just follow us. I think that's the easiest way. And yes.
It's really not that hard. You
Yeah,
go out
yes,
the elevator and go across the hall. It says there's a 13 this way.
Good. And we are going to show probably some easy example that you can just do it by yourself. And then probably we're going to maybe show more in details what Andrew showed us during the demo. And with this, I put some references. The DARPA presentation at DEF CON is on YouTube. That's pretty interesting if you are interested on CGC. I put our emails, some websites, and so we are ready to answer to your questions.
Thank you very much. That is a good thing. You can leave if you absolutely need to. Please be quiet while doing so, and only do it through the stage exit. So keep the voices down. You don't need your voices to leave the room, so that people who want to ask questions can ask questions. So there's a bit of turmoil now. We wait a few seconds until that clears up.
No.
Just for the info, there are how many questions from the internet? Okay, I get that. Okay, to not waste any time for the Q&A, we will just start. So let's have the first question from the front microphone on the right side, please.
Hi, I'm from one of the other teams who have previously participated in DEF CON. My question is, previously it has been kind of hard to get funding for IT security research, at least if you're doing CTF-like stuff. Why do you think DARPA has put this huge amount of money into this cyber challenge? What do you think their motivation for doing that is?
Do you have an answer?
Well, I mean, on one side, I guess you could say that maybe the situation has evolved enough, and I mean, if you follow, for instance, AFL has definitely proven that it can find many bugs almost automatically. If you follow the conferences, you'll see that static analysis has made many improvements. So maybe DARPA thought that it's ripe enough to start challenging people. But I guess ultimately it's a question for DARPA.
Okay, so let's have the next question from the Internet Signal Agent.
Yeah, question from the internet is what kind of answer you got for your Freedom of Information Act request?
So can you repeat the?
In one of the last slides, we saw an example of a Freedom of Information Act request, and the internet was asking if you got an answer on that, or what kind of answer you got.
A Freedom of Information request?
That's what the internet is asking.
I don't know.
The internet is wrong, we think.
Good.
Okay.
I mean, what can I say is that I think after the competition, I think we are going to release most of the code, if not all the code. So, but I don't understand the question. And also, no, another thing, so all the submitted all the binaries that have been submitted for the qualification, and all the patch binaries, all the exploits, they are available on the DARPA website. So if you even want to understand what all the teams did, you can just get those binaries, reverse them, and you can have an idea what teams are doing. And that's all I can say.
Yes, and DARPA also has not all, but most of DARPA's code, such as the Linux modification and so on and so forth, all of that is public. And yeah, so if you want to take a look, I believe at the moment you can get a good look, and certainly after the final, this will probably improve a lot more. So I think there is a good amount of release of information, obviously, I mean, we don't control everything, so, and the competition is still ongoing. So.
Okay, is that a question on my right side, on your left side? No, that's no question. Do you have a question? You're standing? People are just standing. Okay, is there another question from the internet? There's no question from the internet. That would be then the perfect point to wrap up. And oh, there's one microphone question over there.
One last question. Do you think 2 million is a fair price for an automatic exploit creation tool?
Do you need more? Do you think we should get more or less?
I think we should get more.
Yes, this is very difficult, and it's consuming the time of. It could consume the time of all of our researchers. It cannot consume the time of all of our researchers because there are other projects our lab must be doing. But it's an incredibly difficult program. It is tantamount to creating the first. It's not quite the first step to like a Terminator-esque dystopian hacking robot future, but it's very good inroads if you're into that sort of thing.
No, I mean, you're giving them a tool to, with some improvements, exploit almost every binary program for only 2 million.
Well, if anybody in this room would like to talk to DARPA about extending the grand prize, I would be happy to help them with that. But at the moment, even the $750,000 is going to fund Shellphish, going to DEF CON, and eating pizza for the next 20 years.
Okay, then wrap up. So, thank you, Antonio, Jacopo, and Andrew, for this very nice talk, and be sure to join them on their workshop.